In order to fully and elegantly understand how alcohol dehydrogenase works the magic that it does to detoxify alcohol, we really need to go back and understand chemical kinetics. So let's jump right in and look at first order kinetics and just kind of remind ourselves of some of the chemistry involved here. So first order reactions, our knowledge of the chemistry of those can be applied to a biological system by thinking about a reaction catalyzed by an enzyme in which a substrate is converted into a product. Now, if we are just generally thinking about the kinetics of this reaction, we know that the velocity of the reaction is going to need to be equal to the change in the concentration of product over time. So the concentration of P over dt. And we also recognize that, of course, that is correlated with the concentration of substrate. So we could say, yes, there is a correlation between the change in the concentration of product over time with the concentration of the substrate. Now, in order to turn that proportionality into an equality, we need to have a rate constant. So another way that we could write a velocity equation would be a rate constant times the concentration of substrate. Now I'm going to put the exponent there. Of course, we need to remember that the reaction order is in fact experimentally determined, though it typically parallels stoichiometry or often. So now we can kind of think about units on an expression for reaction velocity. We would, of course, expect to see some change in molar concentration over time. So that would indicate then that the units on the because we know that the units on concentration would typically be molarity, the units on the rate constant would have to be 1/2, so that we could get the molarity per second that we would be getting with velocity. Now, if we look really carefully at this equation, velocity is the rate constant times the concentration of the substrate, we actually can recognize this as being a function that's very familiar to us. In fact, this is a y equals mx plus b function, or a linear function. So we could actually jot a graph down in which we're looking then at the y-axis being, of course, the velocity, and the x-axis being the concentration of substrate, and we get a linear function where the intercept is 0 and our slope on the line is equal to the rate constant. So we can recognize then that the kinetic order or kinetic reaction order here is first order. So if you want to give it a try, your next pickup line in the bar could be, if you were a reaction, you'd be first order. Give it a go and see how that goes for you. This curve shows the product concentration and increasing product concentration with time. So notice that we're graphing something completely different than we were graphing on the prior graph. We're now just showing product increasing over time. What you might immediately notice about the function that results here is that it is not linear. That is, we're looking at a hyperbolic function, where what we notice is that as time increases, eventually the amount of product form hits an asymptote where no longer is product substantially accumulated with time. Now, said another way, this means that the reaction is achieving equilibrium as we reach this asymptote. That is, product is formed as quickly as it is consumed. Equilibrium is reached. Let's start out here on this asymptote where the function flattens, and we're now seeing that the increase in product over time is not particularly, it's particularly static at this time. So what happens when the reaction reaches equilibrium is that there suddenly is a contribution from the reverse reaction. That is, we're no longer just seeing substrate going to product. So I'm going to jot this down. At first, we were considering only the reaction by which substrate was converted to product, but we now recognize that in fact this becomes an equilibrium. And with time, the reverse reaction begins to contribute. And we're now looking at an equilibrium being reached where product is now converted back to substrate. We're getting a contribution from the reverse reaction when we hit this flattening point in the curve. We now have two rate constants that are pertinent. Before, only the rate constant, if we looked at the beginning of this curve, only the rate constant describing substrate converted to product was pertinent. But now the K-1, that is the rate constant for the reverse reaction, now becomes poignant. So there are two rate constants that are involved once equilibrium is reached. There may be that there's no more net increase of product with time, particularly if we have reached a true equilibrium where this has truly hit the asymptote. Now, let's contrast this with what was happening at the very beginning of the reaction, in which substrate was converted to product rapidly, and note, linearly. So we've made a dotted line on this graph showing that at the very beginning of the reaction, the only poignant equation is substrate converted to product. There is no extensive contribution, no noteworthy contribution from the reverse reaction at the initial time point. So at this initial time point, we can extrapolate and we can have a linear function that describes initial velocity at the very nascency of the reaction. So at the very beginning, only one rate constant is pertinent, and the concentration of product therefore changes linearly with time. We can simplify this initial time point to being a linear function because there is no substantial contribution from the reverse reaction. So the only pertinent equation at this time point is the substrate getting converted to product, and only K1 matters. So only the rate constant describing the forward reaction is pertinent. We often take advantage of this. That is to say that if we can monitor reactions at their initial velocity and use this linear function to describe these reactions, life is largely simplified. So this simplification is often used, noting that product concentration is going to change linearly at the point of initial velocity. We'll go ahead and jot that down. So we want to monitor the reaction rate at a point where we know substrate concentration and at a point before any contribution is being made from the reverse reaction. We thus monitor the initial velocity, and that is what's shown by this linear function. Marvelous. Let's move along now and talk about when things are not so simple. That is to say, when we get reactions that are not first order and depend upon the concentration of more than one substrate. Now here we can see a reaction that is second order, or often referred to as bimolecular, because of course we have two different substrates. So the reaction would be considered first order in each one of those. So if we were to write a rate equation, we would take the rate constant times concentration of S1, is the concentration of S2. So it's first order in each substrate. So this is an overall second order reaction, which clearly, this gets a little bit more complex, and in fact, even the units on our rate constants for a second order equation are a little more complex, because if we have molar concentration here and molar concentration, let's just be parentheses, concentration here, we get molar squared. So we must have to have rate constant units that are going to be 1 over molar second in order to allow that to come out with the rate expression that we would expect. So this is troublesome. People don't really like it when you have the complexity of a second order reaction. And so in a lot of times in enzyme chemistry, some simplifications get made. And rather than dealing with second order reactions, we will experimentally swamp the reaction in one substrate or another so that it simplifies things. So for example, if we could make it so that S2 is present in extremely high concentrations, like much, much higher than the concentration of S1. So in which case, we can start to express something that we call a pseudo first order reaction. A pseudo first order reactions, simplified because we basically see that S2 is in such high excess that there's no appreciable change in its overall concentration as the reaction proceeds. So now we can express a rate equation in which the S2 is considered to be in zero order. So we can say and in order to just indicate then that this is a pseudo first order equation, we usually just put a little prime on the rate constant. And this just allows for that simplification that because S2 is present in such high concentration, it doesn't change to any appreciable extent as the reaction proceeds. So we like those pseudo first order simplifications. Let's now take our understanding of reaction kinetics and apply it to enzyme kinetics. We had already begun to think a little bit about the equation by which an enzyme binds its substrate, but we're going to return our attention to that equation. And guess what? I also have a wicked cool model that we can look at to hopefully help us envision this. So we have a reaction by which an enzyme binds its substrate. Enzyme plus substrate. And we know that this leads to the formation of the enzyme substrate complex. Now notice that this is described by two rate constants, the one describing the reaction by which an enzyme binds to the substrate, and then the reaction describing the dissociation of the enzyme substrate complex. So noting the fact that this is a reaction that is reversible. Let's then also add, before we write the rate constants for that, let's write the reaction by which enzyme substrate complex becomes enzyme plus product. And we will look at that as a non-reversible reaction, recognizing it at initial velocity, but also recognizing that this is the rate limiting step. So we're going to look at a rate constant for each one of these reactions. The rate constant here, K2, describing the rate limiting step. And then the rate constant K1, of course, describing the forward reaction, and K minus 1, of course, describing the reverse reaction. And I have with me a kind of cheesy demo. You would think nothing less. And so I visited a makerspace in Minneapolis with Faculty Institute last week. And we learned that certainly tennis balls make extremely wonderful enzymes. So here is our enzyme, and maybe it's a lyase, and here's its substrate. So the reaction by which enzyme binds substrate, that would be described by the K1 rate constant. And then, of course, the K minus 1 would be the fact that this is reversible, so the dissociation of the enzyme substrate complex. So here we have enzyme substrate complex, and then here we have dissociated, and that reversibility will be described by those two different rate constants. But then, of course, assuming this is a lyase, the reaction that is rate limiting or catalytic is the one by which this enzyme then makes its two products, and so one product is in my hand and one is in the tennis ball. So there is the products of this reaction, so enzyme plus product. So this is a good visualization then, of course, that second step being the catalytic step, the rate limiting one by which the enzyme worked on the enzyme substrate complex to make enzyme plus products. So let's go ahead and write the labels on this. So recognizing that we have the two separate reactions, this one being the catalytic step and it being rate limiting. And so when we write the rate equation, we're going to consider this as the rate limiting step. And so it will define our rate equation. So this is the catalytic step, rate limiting, this is, of course, the substrate binding step. And let's ready, knowing which one is rate limiting, to write the rate equation. So we recognize that it's going to be defined by the rate constant K2. And so remember when we write that for initial velocity, and of course we're looking at initial velocity, that's going to be the rate constant K2 times the concentration of substrate, which is the enzyme substrate complex. So this defines the rate equation for initial velocity. But we need to look at the fact that enzyme is existing in two different forms in this equation. We know that in total, if we were to express the entire enzyme concentration, or E total, we could talk about that as being equal to the enzyme substrate concentration, that is bound, enzyme bound to substrate, plus the free enzyme. So this would be one way that we could express the total concentration of enzyme. And if we go ahead and make some simplifications, remember when we looked at the way in which we would make something pseudo first order is by swamping it with a certain concentration of one of the reactants. And in this case, if we swamp it with substrate, we can make a simplification, because if there is so much substrate around that all of the enzyme is bound to substrate, we can assume then that enzyme total equals enzyme substrate, and that enzyme free basically approaches zero, because we are swamping it with so much substrate that we can assume that all the substrate or all the enzyme is bound to substrate. So we can make that assumption. So this is termed saturation. And at saturation, we can make all kinds of simplifying assumptions. And in this case, we can estimate then that E total is equal to enzyme substrate. So this is true at saturation. And so the equation that we have up above for initial velocity could be simplified at saturation conditions. So we could say that the rate constant K2 times enzyme total is equal to initial velocity. And you can see how this is a much simpler thing to determine, because it's easy to determine the concentration of enzyme added to a reaction, but it's a little bit harder to know concentration of enzyme substrate. So this allows us an oversimplification. And of course also recognize that we understand that this would, that swamping in the reaction in substrate would enable us to make this pseudo first order with respect to the first and substrate binding step. So hopefully this simplification helps, but please do recognize that this is only at saturation conditions when we have swamped the reaction with excess substrate, so that we can then understand the initial velocity be a function only of the enzyme concentration. Let's take a moment to look at this in the form of a graph, and obviously that visual says 1,000 words.